Hey guys, coming at you with a high octane, riveting content here about Lewis structures, steps that we can use to take a molecule or a polyatomic ion, get the correct Lewis drawing, use something called VESPR to predict its three-dimensional shape. So let's go over some of the things in Lewis that need to be satisfied or at least considered. You need to have a valence total. Everyone's got to have an octet, and just recently added was something called the idea of formal charges. There's a set of rules for formal charges, which is the most acceptable or best configuration has everyone with a formal charge of 0 if possible. Non-opposing charges like a plus and minus on adjacent atoms, and if there is something like a net charge overall that's either plus or minus, the least electronegative element would probably have a 0, and the most electronegative element would have a minus. Finally, there can be octet exceptions, and we call this expanded valence. There are a number of elements that will break the octet rule and form more than 8 total valence electrons around it. And those typically come in row 3, specifically phosphorus, sulfur, and chlorine. Bromine and iodine will do the same thing. And they have unhybridized orbitals that can form extra bonds. More on that later. So let's take a look at an example, and I'll show you how to use VESPR and predict the geometry. Okay, sulfur trioxide. Let's just do the valence total here. We got 6 plus, I like this periodic table because it says 6A. That's an easy way to know. 6 valence electrons. Sulfur's in the same column. So we're going to do 6 plus times 3, which is 18. Okay. So here's my total. Can't exceed that. Let's put the least electronegative element in the center. You would know that because while they're in the same column, sulfur is further down on the periodic table, and thus periodic trends would tell us this is probably less electronegative. So I'm going to put sulfur in the middle. Now, sometimes it's tempting to want to put things in, I don't know, a line kind of like this. Now, one thing that I didn't mention, it's best to avoid these types of situations, and it has to do with the idea of something called steric strain. Yes, that's a real thing. Electronegative elements like oxygen, chlorine, sulfur, if there's more than one of them, best not to put them in a line. They don't like that. The linear configuration is unlikely to exist in nature. What is more stable is something like a central atom that might contain all of them, because when you have them in a line, there's a lot of electronegativity and there's a lot of bending and twisting. Those bonds are strained due to the high electronegativity and repulsion of electronegative elements like oxygen. So I'm going to avoid a configuration like this where possible. I'm just going to go with something that looks like this. Here's the steps that we use. I'm going to give everyone an octet and then add my total. Now, remember, these are just placeholders to see if I have to form multiple bonds. And by counting up all the electrons, I got to get to my valence total, which is usually step 1. So everyone's got the octet now. Let's add up all our dots and dashes. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so when I have 2 too many, I like to remove them from the central atom. They aren't just disappearing. This deficient area is here to tell me that the sulfur is going to need extra electrons, and that one or more lone pairs from the exterior elements can jump in to form a bond. So let's just do that. I'm going to pick the left one for now. Let's pretend like this sulfur jumps down and forms a bond here. Now I know that everyone's got the octet, and I've reached my total, so I'm done, right? Unfortunately, not quite. Let's look at this idea of formal charges. There's an advanced formula, but I'm going to simplify it. All you do is take the element's column number minus the number of outright dots and dashes. So let's do the central element here. Sulfur's in column 6 minus the number of dots. There aren't any. There's only 4 lines. So If I subtract 4, I end up getting the number 2. And so that puts what's called a formal charge on the sulfur. This is not preferable. Let's look at this oxygen. Oxygen is also in column 6, minus 2, 4, 5, 6. This oxygen gets a 0. There is no net charge on this element, or compound. There is on this one, which we'll get to in a minute, but not here. Okay? So what would be the best is if everyone could have a 0. Let's look at these two other exterior oxygen atoms here. Oxygen's in column 6, 2, 4, 6, 7. That's 6 minus 7, and that gives me a negative 1, and that's also going to be a negative 1 here. This amount of formal charges in relative close proximity is not optimal. So what we can do, and what sulfur will do, it'll form more than 8 valence electrons or expanded valence to get all these formal charges to 0. And I know it sounds weird, but sulfur, chlorine, phosphorus, bromine, and iodine are typically the elements you'd see do this. There are in rare situations where noble gases can do this, but we'll get to that later. So here's what's going to happen. I know I've got these odd formal charges that are clustered around here. We can reduce the amount of formal charges by forming a bond here. Now what that's going to do, yes, it will expand the valence, and now sulfur will exceed the octet rule. But sulfur is able to do that because it has unhybridized p orbitals due to its energy level being in row 3. Okay, so what that does is it now reduces the formal charge from this to 0, and now this to plus 1. I have opposing formal charges on adjacent elements. And so the rules of formal charge would say from our previous notes that it's best not to have opposite or opposing formal charges on adjacent elements. And this is what I would have here. So I can have the same situation. Another lone pair is able to form a bond here. And yes, it will look funny because sulfur has way too many valence electrons around it. 2, 4, 6, 8, 10, 12. Sounds weird, but it will happen. And again, that's because sulfur can violate the octet rule in order to become more stable. And in this particular configuration, my formal charges on every single element are net 0, which is the best possible option because I don't have an overall net charge on this particular molecule. Now, let's look at the central atom. We know that everyone's got a 0 formal charge. I'm going to count what's called electron domains or electron dense regions around the central atom, and I can refer to this chart. Unfortunately, you're going to have to memorize this. It won't be pretty, but it's not that difficult. A domain or electron dense region could represent a number of things. An alone pair of electrons? Check. A single bond? Check. A double bond? Yes. And a triple bond. All of those represent electron dense or domains. So on the central atom, I have 1, 2, 3 total domains. I would expect sulfur trioxide to exhibit what's called a trigonal planar geometry because it's got 3 elements that are bonded to it. So this particular molecule would be a trigonal plane. That'd be the predicted geometry. So a better way to draw the Lewis structure would be kind of like this, where I'm putting maximum distance between all the oxygens and all the electrons. If you recall, VESPR stands for valence shell electron pair repulsion. Since they all have negative charges, bonds, and electrons that are unbound, they have like charges and they're going to repel each other. This would be the optimal configuration. Now, this double bond rotating everywhere around these oxygens is going to do a couple things. One, it will compress the bond length. So I would imagine the sulfur trioxide would have a shorter bond length because it has double bonds than, say, another trigonal molecule, maybe something that had, I don't know, something like this. More on that later. So This is the overall entire unit, how to use every step in concert to go from your formula to a Lewis drawing, satisfying all these parameters in between, like formal charges and any exceptions to the octet rule, using the Vesper chart to predict our geometry, and then saying, okay, it's going to be a trigonal planar configuration based on the electron dense regions around the centroid. Hopefully that helps.